This week also have two videos. In this video, we will first learn how to use Wilcox.test. It's a function in R to solve some example problems in chapter 3. Then we will finish the first two sections of chapter 4. So approximately from this slide to slide 48. And then in next video, we will finish the rest part of chapter 4. So let's first look at some example problems in chapter 3. We have introduced how to do the Wilcoxon sign rank tests manually and theoretically. Now let's quickly look at how to use R to do the Wilcoxon tests and also establish the confidence intervals using the wash average. So example 3.1. This example is about given the heart rates of a 7-member group, test if the median equals 70 and the alternative is greater than 70. So it's a one-sided test. And we have introduced that we can get p-values for Wilcoxon test using p-sign rank. But we need to calculate S plus the sum of the positive ranks, and then subtract 1, because here should be the S plus subtract 1, because we want to test the p-value of reaching any value larger than this, the probability of reaching a sum of the signed rank that is larger than this, given the sample size is 7. And because the alternative is greater than, by testing the upper tail, we need to use 1 subtract this p-value to get the alternative, so to get the p-value for the null. If we use Wilcox test, we can define it like this. The first part is x, numeric vector, which should be our data set. We can either, if the sample size is small, we can manually define it like this, or we can input using the CSV or other form of data set. And then we can define it is a two-sided or one-sided. The default is two-sided. So if it's a two-sided test, you can omit this equation and then define the theta 0, the mu, the hypothesized mu value. So if we use Wilcoxon test, let me go there to show this part. So if we go to RStudio, so this gives us the S plus, which is 24. This is the exact S plus, no subtract 1. And then it gives us the exact p-value. So the default is it will calculate the exact p-value. If we define exact equals false, then it gives us the asymptotic value, which is the approximate value. So this is using Wilcox for example 1. And also it will give us the conclusion about whether to reject the null hypothesis. Although this p-value here is slightly larger than 0.05, it still gives us the conclusion the alternative hypothesis is favored, which means the true location should be greater than 70. So how does Wilcox.test come up with this conclusion? It's actually based on p-value and the sample size. So this, because it's a small sample size, it also indicates larger sample size analysis may be appropriate. All right, So then, similarly, we can use Wilcox test for sample 3.2, like this. And for sample 3.2, because it's a two-sided test, if we use p-sign rank to calculate the p-value for two tails, then we need to use a 2 to multiply this value to get the two-sided p-value. All right, then example 3, establish a confidence interval using the 12 female students' heart rate changes when they change position. So we use the, in last lecture, we manually establish a matrix like this using the Walsh average to identify this confidence interval. And if we use Wilcox, it's similar. We just need to define an alternative as two-sided. We do not have to define it because it's default, and then define the mu as the theta 0, the hypothesized median value. And then we need to turn the confidence interval test as true because we want it to return this information. And the default confidence level is 95%. If it's not 95%, then we need to define this conf dot level equals a value we define like 90% or 99%. So anyway, using Wilcox test, it also gives us this result. We can actually test the value of median as well as getting the confidence interval at all at once. All right, before we just use the exact p-value, right? And then let's look at example 3.4 to get a symptotic approximation. So we need to define exact as false if we want to get approximate asymptotic p-value. Otherwise, the default value is true, right? Again, everything else is just the same. But the default is we will use the continuity correction for the data. If we do not want to use the continuity correction, we need to define correct as false. So that we can get a p-value as, we can get the result using the non-continuity correction before the continuity correction. So example 3.5, ranking with ties. We know that Wilcox test does not work for ranks with ties. If we use it, R will also return some results, but it will also return a warning message indicating it doesn't work well for the ranks with ties. In that case, we can also use P sign rank, but again, for P sign rank, we should manually calculate the, not manually, we should get the sum of the positive ranks in advance and only give that as plus. So for this example, if we use P sign rank for both of these two original data, because their P sign, their S plus is different, they will get we will get different p values for them. So example 3.6, what if we still use Wilcox test for ranks with ties? We know we will get a warning message, but we can also get some results like this. Let's say we copy and paste this part. So we will get a S plus, but it's not an integer because in Wilcox it will use some rules such as the mid-rank rule to assign the tied ranks with a value of a signed rank, and then it will calculate the sum of this positive rank. It may not be an integer because of the ties, but then it will give us the p-value. Everything else is the same, but it gives us a warning message like this. All right, so that's all for chapter 3's examples, our code. And then let's move on to start chapter 4. So chapter 4 is about other single sample inferences. Why do we need other inferences? Because sometimes there are other characteristics in our data, or sometimes we demand other findings from data analysis, such as checking distribution assumptions, if they are from specific distributions or distribution families. If the sample is truly random, because we all claim the sample is selected randomly, but we need to sometimes test if they are truly random. And does the data form some trend? Can we get such trend and other patterns? And can we use just counts instead of measurements? When we can just use counts, but when we should better use measurements, etc. So first, let's look at how to match samples to distributions. We know that nonparametric statistics are all about distribution-free statistic tests. But sometimes we still need to know whether our data set follows certain specific distribution or distribution family. So in this section, we deal with test if hypothesized distribution fits the data. Sorry, it's the opposite. Test if our data set fit into a distribution. So one of the methods is called the Kolmogorov test. Kolmogorov test is using the Kolmogorov test statistics to give us the result. So in chapter 1, we used an example 1.1. Two machines produce rods or threads. So we had a sample of diameter data. We compared two different distributions, normal distribution and uniform distribution. How can we check if the data really fits a particular distribution, or if normal or uniform fits the data better, or a distribution family? For example, uniform maybe not a standard uniform distribution, but maybe a piecewise function with two uniform distribution function. But overall, it belongs to uniform distribution family, right? If we want to test those hypotheses, we can use Kolmogorov test. So first, let's recall the Sn function, the sample distribution function, or the step size, the step distribution function. So denoted as Sn. So Sn looks like for uniform distribution, for any distribution, Sn looks like cumulative distribution function, CDF. But it was empirically probability density function, PDF, of a continuous uniform distribution. I mean, this one is not a CDF, right? This one is. So let's say we have a continuous uniform distribution over 0 to 6. This is from a example that we can get a break of on the thread at anywhere, this value is the distance between one end of the thread to the break location. Anyway, we hypothesized it is a uniform distribution, so this value can be anywhere between 0 and 6, and it is a continuous distribution. So, by the way, the integral of a cumulative distribution function CDF should be the probability density function PDF, right? And the integral of this one should be, the integral of this one should be this one. And the opposite is the derivative of CDF should be PDF. All right, and then, and this is the CDF of the same distribution from 0 to 6, and the cumulative probability at the end, at the upper bound, is 1. And if the range of a uniformly distributed variable is from A to B, then the CDF of that uniform distribution should be like this. It's always a triangle, right? And the line is smooth. It's a straight line. And then, so for a standard normal distribution, on the other hand, the CDF looks like this. We can convert any distribution into a standard normal distribution. So it has a z value, and the z value is usually theoretically from the negative infinite to positive infinite. But within the 3 sigma interval, covers 99.999997% of all data. Therefore, it actually looks like all the data is between -3 to +3. So let's look at example 4.1, how to use Kolmogorov to test if a data set follows a particular distribution. So for 6 centimeter threads, we have 20 of them. Breaks can take place anywhere. So they measure the distance from one end of the threads to the breaks and get this data set. So the unit of this data is also centimeters, right? So the value can be between 0 to 6. And then, so let's plot the step function Sx, compare it with the CDF for a uniform distribution. The similar those two are, then the better our data set fits the uniform distribution, right? So since the sample size is 20, Sx increases by 1/20 at each x value, right? Suppose no ties. So, and there are actually no ties in real data. So first we need to order all the observations from the smallest to the biggest as the ascending order. And we have already done that. So the textbook has already done that for us. And then we obtain the Sx of the 20 observations plus Sx of the theoretical lower bound, which is 0, and upper bound, which is 6. So each Sx is 1/20 larger than its previous Sx, right? We can use a table like this to list all the observations with their corresponding Sx. The asteristic means there are repeated observations. So there are 2, 3.4. Therefore, the step size is doubled here, which means the Sx is 2 times 1/20 versus its previous one. And then, so we plot the Sx of the sample data as this steps, this like a stair, and then versus the CDF of a uniform distribution over 0 to 6. The closer the two are, the more similar the distribution is to a uniform distribution, right? Then So let's see the observations we can get. So if a sample comes from a CDF for a uniform distribution, the SX should not depart markedly from CDF FX, right? If the sample is uniformly distributed, then half of the observations should be in the lower half range, and the other half should be in the upper half, right? This is not only uniformly distributed, this is actually symmetric distributed, but which means if that's the case, then S3, when X equals 3, S3 should be some value very close to 0.5, right? Let's say 0.5 is right here, and S3 is here, but S3 is a lot larger than 0.3. Intuitively, this is not a very good fit. So how to evaluate what is a good fit, what is not? Then for Kolmogorov test, we use maximum difference in magnitude between Fz and Sx. So Fz is the theoretical CDF. We use Z to separate with X. X is our real observations. So this Z's may not be just this X because we have only 20 observations. But this Fz is actually a continuous smooth line. So that's the difference. Okay, Fz is the CDF of the distribution that we hypothesized. Then we compare Fz and Sx with a tabulated value to assess the goodness of the fit. We can also use computer software to calculate the exact p-value of this fitness. So we can use a table like this, table 4.2, to list all the X, all the Fx, the CDF, and then as the Sx, the step function, and then we list the discrepancies between Fx and Sx. And because of the stepwise nature of Sx, we also can use Fxi to compare with Sxi minus 1, which means we use each Fx to compare this part and this part to avoid the inaccuracy brought by the stepwise nature. So overall, we go each breakpoint along the way. There are more, there are some Sx above Fx, and also there are some below, but more Sx above, right? So overall, Sx lies above Fx for much of the time, more time. Then the greatest magnitude is, let's see, table 4.2, sorry, table 4.2. The magnitude, the biggest magnitude for both this column and this column is this one here, negative 0.18. And then we have a tabulate to indicate what value should we consider it exceeds the confidence interval. Yeah, we have gone through this. Okay. Maybe not here. So published tables give values maximum differences required for the significance of 5% and 1%. These are alpha, right? And also they give different percent levels for various n sample size. We can look up those tables, but nowadays we usually use the software packages to calculate those. So we do not actually need those tables. It returns sorry, for a significance level as 5%, the statistic should be 0.294, which means the biggest magnitude. If they exceed this value, then we conclude we need to reject the null. Now, our biggest magnitude is negative 0.18. The absolute value is lower than this this critical value. Therefore, we do not reject the null. We still conclude it's an okay fit. This one. All right, and let's jump to slide 33. Comments, a two-sided test is appropriate if the alternative specifies that the observations come from any unspecified distribution. So sometimes the alternative to the CDF must either lie wholly above or wholly below. So we can turn to the alternative. So you can get one-sided test. Then figure 4.5, this figure here, figure 4.5 did not show a good fit, although we failed to reject the null, but intuitively this is not quite a good fit, right? And so some software packages only gives the asymptotic results for the Kolmogorov test statistic, and the sample size should be large enough, 20 or more. So in R, there is Kolmogorov smart test, ks.test, and you can explore more here. It actually is about the KS test here. So KS is short for Kolmogorov Smirnov test. This KS is an extension of Kolmogorov. You can explore more here. And then let's continue. If we use KS test for the same data, and then it gives us this result. The D is the max magnitude, and p-value is this one. So it's not very, it's a p-value that we cannot reject the null, right? So in summary, Kolmogorov test actually waste some information because we only pick up the largest magnitude. So it is feasible that we can actually pick up multiple places to compare the differences, not just the max difference, right? But tests for other differences tend to have fewer advantages. The advantage of Kolmogorov is, although it wastes some time, it is very straightforward and easy to make a conclusion. But for discrete distributions, Kolmogorov tests don't work very well because of the sparsity of the data. So regarding confidence regions, in figure 4.5, we conclude that a 95% confidence region is when the step function everywhere at a 0.294 units depart from the CDF. It's actually a big departure, and even the distribution doesn't fit very well, we still don't get that large discrepancy. Our biggest magnitude is only 0.18. So, which means this confidence regions is actually useless, somehow useless. right? If we weight the magnitude exceeds, the biggest magnitude exceeds this value, or we should say Kolmogorov test statistic exceeds this value, then that's a big discrepancy. If even intuitively we can conclude the distribution doesn't fit. So this interval is not very effective. So if we want to know which distribution fits the best, a better way to do it is use Kolmogorov test on multiple distributions. For example, in real life, a lot of data sets may not follow only one standard distribution. There are maybe piecewise functions to describe the data set. And it belongs to a distribution family instead of a standard distribution. For example, example 4.3, we can use Kolmogorov to test the two hypothesized distributions. First is the null distribution, a uniform distribution over 0 to 6. And second is the alternative, a distribution with two pieces, and for the lower half, the CDF, the cumulative distribution function is x over 5. It's a variance of the uniform distribution, right? And the upper half from 3 to 6, the CDF is using this function. So let's test which one fits better. So for testing the null, all the results are already given in the previous example, right? So to test the alternative, the second case, we can make a graph just using the same procedures of the previous example. So the format was suggested by Ross, so we can also call it Ross graph. We listed the deviation of all Sx from the CDF for both the null and alternative. And we use D1 and D2 to represent the deviations of the two cases. So we finally plot some graph like this. Okay, let's go them step by step. Then in table 4.3, this table, we listed all the observations, the Sx, and then we listed the deviation of the two cases. So the maximum D1 is negative 0.18 here, and maximum D2 is positive 0.12. This one is a little bit closer than this one versus the CDF. So then we can visualize the table information on this graph, the Ross graph. So we plot the deviation for the two cases. And case 1 is a bold line, this one. Case 2 is a lighter line, it's a thin line, this. Intuitively, we think that case 2 is slightly better, right? Fit. So, and those two dashed lines here are the critical region using a 95% confidence interval. So if any deviation point exceeds one of these two dashed lines here, then we should reject the hypothesis, right? But since both of them are inside, all of the deviations of both of the cases are inside those two dashed lines, the critical region lines, then we fail to reject the null. We fail to reject either the null or alternative. So we kind of have a useful comparisons here. Although they are different throughout this range, for some subranges, case 1 is closer to 0. But for more subranges, for more area, the case 2 is much closer to the 0, which is no deviation from the guessed CDF. There are two hypothesized the CDFs are different, but here we only show the deviation between each observation and the their own hypothesized CDF. So from the we can conclude that although both of them are not falling outside the critical region, case 2 fits slightly better, right? Conclusion, there's no strong evidence against either of the two distributions, but case 2 may be a slightly better fit. Kolmogorov test only works for complete, specified, continuous distribution. So in other words, we have to specify a hypothesized distribution so we can plot our data against it and use the Kolmogorov to make a conclusion. If we specify the sample has a normal distribution with estimate mean and variance, then we can also use Kolmogorov test, but the p-values are not exact, but asymptotic, approximate, and that requires the sample size to be large enough. So then we have some alternative method for testing normality. It's called Lillefer test. So Lillefer test assumes observations are from unspecified continuous distribution, and we test whether it is a member of the normal family. So to this extent, Lillefer test is not distribution free, right? But it is nonparametric because we do not specify parameters. So this method can be extended to test the capacity of a dataset with other families also. Another method to test the normality is named the Shapiro-Wilk test. We can use R to perform both tests. Here are some links. And also, why do we have different methods? Because they are good at in different situations. They may work well. So please find them out by yourself, and we'll go through that in next lecture. So let's look at one more example. Remember the example of death ages for 4 clans. So the data is in Appendix 1, right? Then from all 117 observations, those are the death ages for all 4 clans. So people randomly select 30 from them and then put them in ascending order. And let's test their normality. Lillefer test is comparing the standard normal CDF, phi-z, with the standardized sample CDF, SZ. So please read the details of the example 4.4 in textbook. And that's for the first part of lecture this week.